recording. So we are now continuing the lecture of the op-amp, the properties of ideal operational amplifier that we discussed last class. We'll continue from here. So what we have seen in the last class, that what is the meaning of an op-amp being saturated. Just a quick reminder that whenever an op-amp is saturated, it essentially means that the output of the op-amp has become equal to the terminal or the maximum value of the supply voltage. Why do we call it a saturation, or why the state of saturation is in most cases unexpected for us? There is a problem for saturation. Saturation problem ta hocche erokom. Let's say if we take a look at these examples over here. Let's say if we take example 1, you can see over here that the V plus had a value of 1.4, V minus has a value of 1.3, and then the mathematical calculated output was 10,000 volts, which is definitely impossible. So in this case, the output was plus 9.0 volt. This was the output for this op-amp for this setup of input and the setup. Now, what is pretty important for you to understand that the purpose of an amplifier for most of its operation, is to provide an amplification. It means you give it a weak voltage or a weak signal, it will increase that signal or weak voltage into a proportionally larger voltage. That is the purpose of an operational amplifier. Now, whenever any op-amp becomes saturated, it cannot process change of the input. What I mean is something like this. Let's say in this scenario, our V plus, let me write, our V plus was 1.4 volt and V minus was 1.3 volt. And the V out was calculated to be 10,000 volt. That was the scenario over here. Now, if by some happening, if this V plus increases from 1.4 to let's say 1.41 volt, so there is a change of the V plus value. So one of the input is undergoing some sort of change. In this case, if we do the calculation over here, this V out, the mathematical output of V out would be somewhat bigger. I think this would be 11000 volt, something like that. The mathematical calculation is giving us this value for a certain small increase of this output. Now, what is going to happen for the realistic output or for the actual practical use of the op-amp? This situation of this pair of values gave us an output of plus 9.0 volt. This calculation output would also give us plus 9.0 volt. So the problem that we are coming across is that a change in one of the inputs is not reflected proportionally on the output side. You do have a bit of a change in the input side, but because the op-amp becomes saturated, it does not have the capability to reflect that change onto the op-amp, which means that it cannot actually do the amplification, the key purpose for which is used, for which an op-amp is used for most of its performances. It is a problem. Arta problem hoche, it is a key problem. Now, if you wonder that, what is the useful range for the op-amp to be useful, for the op-amp to be for the op-amp to avoid saturation, we can actually find that out. You see that the typical value for the gain of an op-amp, of a typical op-amp, is about 10 to the power 5, and in this case the supply was plus minus 9 volt. So if we take one on the terminal value for the supply voltage and try to do some reverse calculation, for example, let's say if I write this equation that V out equals to A naught, which is gain, into V in. So if we want to have the output to be 9 volts, this is the maximum value of the output that you can have, plus or minus, doesn't matter. That should be equals to 10 to the power minus 10 to the power 5 into V in. Or in other words, you can write V in should be equals to 9 into 10 to the power minus 5 volts, which means the difference of V plus minus V minus, this value, the difference of these two inputs should be at maximum 0.1234. The difference between these two voltages should be maximum this much big. This much big means what? That this input voltage value, if the difference of the two input voltages, V plus and V minus, is maximum this much, which means either smaller than this or at max this much, then the output can have a variation from 0 volt to 9 volt. So having a this much small variation means that the actual operating capability for the operational amplifier or the range of the inputs have to be extremely close, like super close. I mean, having a difference of this much is almost having no difference at all, but this actually means a difference. So as long as these two values are extremely close to each other, so that even when we multiply that very small difference with a multiplier of gain, which is about 10 to the power 5, then we can get the output to be 9 volts. So if the V plus and V minus difference, if this difference is up to this much range or smaller than this, then we can say the operational amplifier is not saturated, which means for this much difference, the operational amplifier can exhibit its behavior of amplification. Now, this is something that is difficult for the operational amplifier to work with. So there is a mechanism by which we actually get rid of this trouble, that how can we avoid saturation. So there is a practical way how we can avoid the saturation, which is called negative feedback. We're going to talk about that after a while, how the saturation is avoided. But that's a bit far-fetched. So I'm just to Hindi raklam je there are ways by which we can effectively overcome the saturation of an operational amplifier.
Sir, এখানে A naught দিয়ে আপনি কি রিপ্রেজেন্ট করতেছিলেন?
First দুটো প্যারাগ্রাফ পড়ো, have a look.
স্যার ওপেন লুপ গেইন মানে বুঝলাম না ব্যাপারটা। So basically it is the ratio between the output voltage and input voltage, sir.
Sorry, I muted my microphone because I was sneezing and I forgot to unmute myself. So hey, yeah, it is actually the ratio. Gain is the ratio between the output voltage and the input voltage. So yeah, that's basically it. বুঝা গেছে?
স্যার ওরা আবার ইনভার্টেড, মানে আমি আসলে এই অপ অ্যাম্পের ব্যাপারটা বুঝলাম না, বিকজ অ্যাপ্লিকেশন লাস্ট ক্লাস মনে করি নাই দেখে মনে হয় এই প্রবলেমটা হচ্ছে।
তুমি গত ক্লাস করো নাই?
না স্যার, পরীক্ষা ছিল স্কুলে, এই কারণে আমি আর কি গ্যাপ দিছিলাম।
আচ্ছা, সমস্যা নাই, ফলো আপ। আমি ক্লাস আমি অ্যাকচুয়ালি আপলোড করছি কি ফার্স্ট ক্লাস আমি আপলোড করি নাই। I still have it in my PC. আজকে আমি দুটো আপলোড করে দেব।
স্যার করছেন তো ডাইরেক্ট সেন্সিং এর অপ অ্যাম্প লেকচার।
বুঝি না কি বলছ আবিয়াস?
ডাইরেক্ট সেন্সিং অপ অ্যাম্প লেকচারটা আপলোড করেছেন তো ইউটিউবে।
করছি, আমার লেকচার আপলোড করা হয়েছে।
জি স্যার।
Okay, so these are the two properties that we have talked about. Is that one is the infinite input impedance, the second one is the infinite open loop gain. The third property that we are going to talk about is zero output impedance. What does that mean? I'm going to take this picture out onto the note. So this is the typical circuit symbol for the operational amplifier. So to represent the first property, what I asked you to understand that no matter how big is the voltage difference between these two input sides, there will be no current flow in this path. Let me use red. There will be no current flow within this path, which tells us that there is an infinite input impedance. No current flow will happen through any of the inputs, irrespective of the value of the voltage. The second property was infinite open loop gain, which means the theoretical value for an ideal op-amp gain is infinite, which means even if there is a very small difference between the inverting and the non-inverting inputs, the output will become saturated. And we just talked about the saturation a bit detailed more than the last class. The third property is that zero output impedance. Zero output impedance means if we have applied some voltages over here, you have to understand that this voltage would be available on the output side by the process of amplification. The idea of zero output impedance means that whenever this voltage would be made available, either the positive voltage made available on the output side or the negative voltage made available to the output side, any of those, this voltage as it is made available on the output side will not experience any reduction, as this will be transferred from this input location taken to this output location. What I'm trying to mean over here, try to understand. Voltage is not actually, voltage doesn't walk from one place to another place like current. Voltage is actually the push of or pressure on charges to flow from one place to another place. So whenever you are trying to have the voltage from this place to this place, if you want to have the exactly same equal voltage, it means whatever these two wires are connected in between, so whatever that lies within this op-amp structure to connect this end with the output side or the negative supply with the output side, these parts do not have any resistance whatsoever. What I mean is this. Let me use a opposite version of the explanation. Let's say by some mathematical calculation, we are finding out that the output of an op-amp is going to be, let's say, plus 8.2 volt. Let's say this is the value that we have calculated. Now the supply is, let's say, plus minus 9 volts. This is plus 9 volts, this is minus 9 volts, which means in this case the output is supposed to be 8.2 volt. Now, practically speaking, when this 8.2 volt output, calculated output, should be drained from here and be made available over here, in practical scenarios, whatever that is responsible to carry this voltage information out to here, this might actually cause some voltage drop, because there is no such electrical thing except for superconductors which have zero resistance. But the property of an ideal op-amp is that no, there will be no resistance whatsoever, or the impedance of these connections, either from positive supply to the output or from the negative supply to the output, these connections will have zero impedance whatsoever, which means whatever that we have calculated, this exact value will be made available as the output. So no voltage drop from the supply to the output side. That's the meaning of the third point. So might as well take those information and take it on, paste it on my thing.
So basically input voltage 8.2 volts, right?
Nah. The calculated output was 8.2 volt. That's what I'm proposing for
So
calculation.
how did we like lose the volt?
We did not lose the volt. It is the magnification factor that is giving us that output. আচ্ছা এটা এখানে রাখি, এখানে রাখলে দেখতে একটু easier হবে. So infinite impedance is covered in open loop gain, zero output impedance. এই পার্টটা বুঝা গেছে? I'll go through it again. Infinite input impedance means there is infinite resistance between the two input parts, so no current flow through them, no matter how much is the voltage across these 2 points. Infinite open loop gain means even a very small input voltage or even a very small difference between the two inputs of the op-amp, the output will become saturated. The third point, zero output impedance, means whatever is the calculated value or the whole output voltage is provided across the output lane. This is actually the meaning of this thing. So the calculated value of the op-amp will be made available on the output side, and there will be no loss of voltage within the op-amp circuitry. Then it has, they have these 2 points. These two are actually pretty simple. I'm not going to explain the visualization for these parts in a very high rate, but these are pretty simple to remember. Infinite bandwidth means an ideal op-amp is capable to work with all sorts of frequency of alternating voltages. So what does this mean? Let me give you a simple idea. Let's say we want the output to vary as the input undergoes some variation. Let me give you a simple idea. Let's say we have connected a diode and an LED over here, which has a rated voltage of, let's say, 9 volt, and we have connected one of the inputs to ground, and here is a 9 volt supply, which means this diode, if this diode gets plus and minus like this, it will glow. If it's the other way around, it will not glow. So we might as well connect this to the ground as well, which means if this is a high voltage plus 9 volt, then current can flow from 9 to 0, the diode will glow. If the reverse thing happens, if this side is minus 9 and this side is always 0 because it's connected to the ground, then current will not flow. And let's say here we are going to connect an AC supply. So we're going to connect an AC supply over here. So let me take that AC supply. Let's say this is a AC supply, and just because AC supply should have both of the ends connected, so we can connect this end to the ground as well. So this AC supply will be providing the voltage over here. So because this is the zero side, so if I write this AC supply as, let's say, this is a 1 millivolt AC supply. 1 millivolt AC supply means if we have connected one of the AC supply to the ground, then this other side will be swapping from plus 1 millivolt to minus 1 millivolt, and it will swap back and forth within those two terminal values, which means in this case our actual input V in will be varying with this much value, because V in input voltage is given by the difference of V plus minus V minus. In this case, V plus is considered to be 0 volt. That's how I designed it. It could be other way around as well. I'm just making a simple representation for how this can work. So V plus can be 0 volt, and V minus can be alternately plus 1 millivolt, or it can be minus 1 millivolt. So input can be plus 1 millivolt, or input can be minus 1 millivolt, vice versa. So this would lead the output to be plus minus 9 volt. Every single time the output is positive, this LED will glow because it will be in forward bias. If the output is reversed, it means if the output of the op-amp is minus 9 volt, then this LED will not glow. Which brings us to a pretty interesting scenario. If the frequency of this input source is, let's say, 10 hertz, which means the variation of these voltages happen every 10 seconds, so 10 times every second, then this LED should also glow 10 times every second. So it will make 10 blinks per second. Does it make sense?
Yes, sir.
That if the input is undergoing a variation of 10 hertz, then that would create a variation of that output of 10 hertz, but with a bigger voltage, because it's going to take the voltage from the supply. But we can have the similar frequency available. Let's say, fine, beautiful. If the input voltage is, let's say, 10 to the power 2 hertz, 100 hertz, it should have 100 hertz. So this idea of infinite bandwidth means that no matter what the frequency of the input side is for an alternating supply, even if it has infinite frequency, this op-amp is capable to handle that variation and actually reflect that frequency on the output side. So what it's saying, that if the input side frequency variation is extremely large, the ideal op-amp is capable to give an output with the exact same frequency. So it would not have any problem to handle any amount of frequency of alternating voltage to reflect onto the output side, which is not practical because these are made from physical components. Whenever we are actually reversing the voltage, electrons have to decelerate to stop and then start to flow in the backward, in reverse direction. Then whenever we reverse the voltage again, then they have to decelerate to stop and then start to flow in the reverse direction. So every single time the electrons have to go back and forth by the application of reverse voltages. That's a physical mass which have some sort of inertia that we're talking about, flowing through a conductor that we're talking about. Because it's a property of the ideal op-amp. You have to understand this, that the ideal operational amplifier has a property that is infinite slew rate, but it means it is not actually practical. Practical op-amps, on the other hand, has a range or a limited value of bandwidth for how much they can work. Have a look. It says that Real operation amplifiers deviate from the ideal, obviously. In practice, the input impedance is usually between 10 to the power 6 ohm and 10 to the power 12 ohm. So it means it is a pretty high value of impedance. It's not essentially infinite. And output impedance is about 10 to the power 2 ohm. So that's not essentially close to zero, but it's significantly smaller compared to that. Then it says the open loop gain is usually about 10 to the power 5 for constant voltages. The slew rate is this thing. I didn't talk about the slew rate, so I'm going to talk about the slew rate after a while. And bandwidth are not infinite. Bandwidths are not infinite means that, well, here they have not mentioned a practical range for the op amps. I think that can actually vary very widely. That's why maybe they haven't mentioned a typical value. But bandwidths are not infinite. It's impossible for a physical device to be able to handle infinite frequency of alternating voltage. That's physically not possible. But that's the idea for an ideal op amp. All right. The fifth point says infinite slew rate. Infinite slew rate means there is no delay between the changes in the input and the consequent changes in the output. This means an ideal op amp has zero reaction time. I'll say it again, try to absorb the information. An ideal op amp has zero reaction time. What could you possibly mean from here? An ideal op amp has zero reaction time. What could this possibly mean?
তার মানে নেগলিজিবল টাইম ডিউরেশনের ভেতরে ইনপুট থেকে আউটপুটে কনভার্ট করতেছে আর কি।
Exactly. Ideal op amp negligible na. Ideal op amp, which is obviously a hypothetical idea, it has infinite slew rate. It means it has no delay between the change of the input side and the available change in the output side. It will be instantaneous. But practical op amps don't act that fast. They have some limitation. For example, in this case, this practical, let me explain what does this mean. About 10 volt per microsecond. This means that if you are applying some voltage variation onto the input side, let me give this with some sort of graph, maybe might help. Let's say on the input side, if we connect one of the inputs at a 0 volt and connect the other end to the AC supply, this is just to time. And let's say if this I'm plotting with just to microsecond, and let's say if the input voltage is gonna vary, let's say up to plus minus 20 volt. It's pretty large value, I understand, but bear with me. Is it for input or is it for output? আচ্ছা না, sorry, it is for output. My bad. এটা আচ্ছা, আমি এখানে ভি আউট লিখে দিই, তাহলেই হবে। আমি বুঝাচ্ছি তোমাদেরকে, ডোন্ট ওয়ারি। Just a second. So let's say for an op amp, the output voltage is going to vary from plus minus 20, which means let's say the supply that we're providing to the op amp is of plus minus 20 volts. Now, how can you get a plus minus 20 volt supply? I'm going to show you that using a circuit. Just after a while, it will show up in our comparator circuit. Now, the slew rate information means that whenever the output will change, for every 10 volt variation of the output, a practical op amp would require 1 microsecond amount of time, which is sort of like an acceleration value for the op amp to handle. So what I mean, let's say the input signal is changing with, let's say, 2 microseconds. So let's say this is a microsecond scale. Here is 1 microsecond, and here is 2 microsecond. Let's say the V in that is undergoing some change. I'm not giving values over here because I'm considering an ideal op amp, which means it's going to be saturated at 20 volt whatsoever, or it's going to at least try to become saturated at 20 volts whatsoever. So if the input has a variation like this, which has a time period of 2 microseconds, so we're having one of the cycle in 1 microsecond, it means this op amp is capable to show 10 volt of variation in 1 microsecond. So this is what's going to happen. Whenever, let's say, the op amp voltage output starts from 0. When this is starting to increase in 1 microsecond, when this 1 microsecond is finished, within this entire duration, this output voltage is supposed to go up, because this Vin in this case is positive. Positive Vin means output should also be positive, and because I'm considering infinite open loop gain, so output should become saturated. Here's the deal: should become saturated. This is a time frame with respect to a microsecond. Now, output is supposed to increase, but an ideal op amp would have instant increase. The moment this becomes anything positive above 0, an ideal op amp will immediately reach 20 and remain 20 for the first 1 microsecond. And the instant the input becomes negative, then the output will become flat negative 20 and remain negative 20 for the next half cycle. This is how an ideal op amp should behave. Ideal op amp, which has infinite slew rate, or it doesn't have any delay between the input and the output side. This is for the ideal case. So what happens for a practical op amp? It has a slew rate of about 10 volt per microsecond, which means it can handle 10 volt of variation of voltage under every microsecond. Now here's the deal: whenever this voltage is going up, or it is actually positive for this whole duration, the op amp output is going to try to give us positive output. So that output will start to increase from 0, and within the first 1 microsecond, it will be only capable to rise. Let's say, I'm not sure about the shape, so I'm going to give a linear shape, but I'm not very sure about that. So if this is plus 10, if this is plus 10,
ব্লু গ্রাফটা কিসের জন্য বলবেন?
practical or realistic op amp এর জন্য. So if this is a plus 10 value, a real op amp within the first 1 microsecond will rise up to here, because the time frame is so small, because it can only react up to 10 volt of output variation within a time space of 1 microsecond. So it wouldn't be able to reach up to 20 volt, because it simply does not have that much reaction, small reaction. It cannot respond that quickly. It is trying to go up, but it cannot rise that fast. And then whenever this op amp part is gonna actually start go down, then this voltage has to become 0. This voltage has to become 0, and it should represent as negative. But here's the deal, here's the problem. This thing is once again having a downward cycle of how much? Exactly 1 microsecond, which means to reduce to 0 and to become negative, this downward cycle as well, the op amp only has 1 microsecond. So within this 1 microsecond, the mathematically speaking, this positive voltage should become 0 and should once again become minus 20. But that's not going to happen, because the op amp can only change 10 volt of output every 1 microsecond, which means in this case, this 10 volt plus 10 volt will simply have enough time to reduce to 0. By the moment this has come to 0, this output, this input will once again become positive, which means it will no longer have the incentive to go negative. It will once again start to go positive like that. So in this case, we are not going to have a negative output whatsoever, because the op amp cannot simply handle that much high frequency. 1 microsecond, 2 microsecond time period means a extremely high frequency. Can someone tell me the frequency of this thing? 1 by 2 × 10⁻⁶. এটা কত হয়? I think 50,000 hertz. Am I correct?
Should be 0.5 × 10⁻⁶.
Yeah, 50,000 hertz. So if you are feeding this input an AC supply of 50,000 hertz, then the output would run through this kind of trouble. The reason being, that the op-amp simply cannot handle to give us that much change. This is a typical practical scenario. I tried to show you this. You will never be asked questions about this graph. I tried to show you this graph to give you a significance of what this information mean. That 10 volt per microsecond, it means the op-amp can handle a variation of 10 volt on its output side for every microsecond duration time, or in other words, I can say that in one microsecond duration of time, it can change a maximum of 10 volt output value. So এই জিনিসটা বুঝা গেছে কিনা বলবান, মানে 10 ভোল্ট পার মাইক্রোসেকেন্ড এই জিনিসটা আইডিয়াটা বুঝা গেছে কিনা? Maybe not.
Sir,
Can you repeat?
I can. কোনখান থেকে রিপিট করব? কত বন্ধু বুঝছো সেটা বলো।
The hertz part where you 1/2 times 10⁻⁶. Why did you do this? For which part?
মানে this one?
Yes, sir.
Oh, I was just trying to show you that if an input voltage has a frequency, has a time period of only 2 microseconds, then how much frequency of an AC supply that we're talking about? It means that this AC supply that we're handling here has a frequency of 50,000 hertz. A practical op-amp cannot respond to that kind of a highly varying or rapidly varying input to represent the actual behavior that it is supposed to give us on the output side, because it cannot change its output that fast as the input is changing. Or in other words, you can sort of think like that this is a representation of the, let's say, the hysteresis, sort of like the hysteresis inside the op-amp, that it cannot react to that rapid amount of change, to the rapid rate of change on the output side, because it can only change up to 10 volt per microsecond. So within the duration of 1 microsecond, the output can have a maximum variation of 10 volt. That's why.
Thank you, sir.
আচ্ছা, এখানে আরেকটা জিনিস তোমাদেরকে বলি। ফর এক্সাম্পল, আচ্ছা না, I should not actually make this more complicated. Abias, you are about to say something?
Sir, why does it only rise to 10 volts?
Because this time duration is 1 microsecond. It can only make a maximum amount of change
for
of
the
10 volt within 1 microsecond.
So if the input was say 5 volts, then it would be able to handle that.
Then it will rise up to 10 volt within half microsecond. It will rise up to 5 volt within half microsecond and maintain 5 volt for the next half microsecond.
That makes sense, sir.
বুঝছো?
Yes, sir.
আচ্ছা, সো এটা গেল।
স্যার,
হ্যাঁ বল শুভ।
আমি একটা জিনিস ভাবছিলাম কি, যে আইডিয়াল অ্যাম্প মিটার তো আমরা কনসিডার করি যে মানে ইনপুট ভোল্টেজ বেসিক্যালি যেটা আসবে আউটপুটেও বেসিক্যালি ওইটাই আসবে, রাইট? কারণ আউটপুটটা যেহেতু আপনি বলছেন যে স্যাচুরেটেড।
না 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 না, ইনপুটে যত ছোটই হোক না কেন আউটপুটটা সাপ্লাইয়ের সমান হবে। আউটপুটটা ইনপুটের সমান হবে না। Input can be very small and input is usually very small. The output will become equal to the supply voltage. That's what saturation means.
মানে বেসিক্যালি অ্যাকচুয়াল যে মানে is it like the input voltage মানে for what reason is it becoming less than the supply voltage?
মানে are you asking the মানে mechanism what happens in the op-amp for which we have this kind of output? Is that the question?
Yes sir, ওইটাই আমি মানে ইনপুটটা কেন আসলে পাওয়ার সাপ্লাই থেকে কমে যাচ্ছে, তারপর আবার কেন এটাকে চেঞ্জ করতে হচ্ছে, that is the thing, right?
Input is not having any change based upon the op-amp. Input is fed from a physical device, and that is amplified using the op-amp. Input is not dependent on the op-amp. Input is the independent input, and op-amp amplifies that voltage, taking help from the supply voltage to amplify the input.
বেসিক্যালি স্যার সাপ্লাই ভোল্টেজ যাই থাকুক, ইনপুট একটা পার্টিকুলার ফিক্সড মানে লো অ্যামাউন্টে থাকবে?
No, input can undergo change based upon the type of input that you provide. It can be a DC supply, it can be an AC supply, it can be a different amount of supply from LDR thermistor or metal wire strain gauge or a piezoelectric transducer. It can come from a lot of different input variations, and it can have alternating behavior as well. আচ্ছা, এরপরে আমরা জিনিসটা দেখবো সেটা হচ্ছে what are the typical usage of an ideal operational amplifier. Acha, before I will print this out, I should actually label this thing. তোমাদের সিলেবাসে অপারেশন অ্যাম্পলিফায়ারের বেসিক 3 টাইপের সার্কিট আমাদের হ্যান্ডেল করতে হবে. We have to handle exclusively 3 type of circuits for operation amplifier. Your primary job would be to look at the circuit and be immediately able to detect what kind of circuit are we talking about, because only after you detect what circuit are you handling, you can choose the set of formula that you can use for that circuit, because for different of the circuits we have different set of formulae. So the first circuit that we are working over here is what is called a comparator circuit. So this is the comparator circuit looks like. I'm going to explain this in detail. Have a look. Candidates should be able to deduce from the properties of an ideal operational amplifier the use of an operational amplifier as a comparator. Actually, one thing I should also mention, for all the mathematical questions of your syllabus, you will be always handling with ideal op-amp. So you don't have to take into effect the practical problems that practical or real op-amps have. But what kind of problem might we have if we have a practical op-amp in the place of an ideal op-amp? These kind of questions might show up in explanation type of question. So for mathematical calculation, we'll be always considering ideal op-amp for the sake of simplicity. But what if this was not an ideal op-amp and it was a real op-amp? What kind of variation do you expect? So you can have 2-3 marks of question of descriptive or explanation type of questions from those things. It's very much similar like the projectile question that you come across. We consider that error is negligible. Then at the end of the projectile question, there shows that what if error was not negligible? Draw a curved line or trajectory for that, and you have 1 or 2 marks for that. Something like this. So mathematical questions will be always handled with ideal op-amp. But if ideal op-amp was not present, it was a real op-amp, what kind of variation would you expect? That kind of questions can show up as per explanation-based question. It is possible. Okay. So let me explain this part of the circuit. The first thing that I would like all of you, to take a good look, that this point over here does not represent an elliptical connection. This represents an overlap. এই জিনিসটাকে ভালো করে মাথায় ঢুকাও. I'll take out this circuit so that I can draw upon it. All right. The first thing that I want you to appreciate is that this point right over here, this one represents an elliptical overlap, not elliptical connection. This is a comparator circuit, means we'll be applying some sort of voltage onto the 2 input sides. So those voltages are shown with respect to a 0 volt line or an arc line. So this line in the middle is represented as a 0 volt line, or this is 0 volt, and whatever the value of V minus with respect to this one is represented as the V minus, this is represented as V plus. The arrow lengths are not to scale, so you don't have to assume that in this case V minus is big and V plus is big. It could be any one of those. But you have to understand one thing, that typically if we have similar directional arrows for a voltage symbol in a circuit, they mean they are similar voltage. It means in this case either both of them are positive voltage or both of them are negative voltage. They are not opposite type. So this arrow direction actually mean one of this information, which is pretty important. The arrow lengths do not actually mean the value of those things, but the direction of the arrow represents the type of voltage. Similar direction arrow in a circuit mean similar type of voltage, both positive or both negative. That's very important information. Now let me explain the usefulness of 2 set of battery over here. Have a look. Let's consider that this battery is rated for 9 volt. Just a simple example. This is the positive end of the battery, this is the negative end of the battery. We have connected this negative end of the battery to the 0 volt side, which means this entire wire is currently 0 volt, which means this would cause this end to become plus 9 volt because the difference between the two plates of the battery has to be 9 volt. Vice versa, and we have connected this plus volt onto the positive supply end, which means this supply in this case is plus 9 volt supply in. We need to provide an equal amount of negative supply on the other side as well. So what are we doing? We're taking another of this battery. This is also 9 volt. We've connected the positive end with the ground line, which means the negative side is now becoming minus 9 volt because the difference between these two plates has to be 9 volt. This is the high voltage side, which is defined to be 0 volt. So the low voltage side has to be 9 volt, minus 9 volt. And we are feeding this voltage to the negative supply. As a result, this is becoming minus 9 volt. So the purpose of these two batteries, along with the ground line, is to make sure that we can have plus minus 9 volt input to the supply of the, not, I shouldn't use the term input, we can have plus minus 9 volt supply into the op-amp device. এই rectangular circuit purpose টুকু বুঝছো কিনা? Why do you have two set of batteries and what's the purpose of the ground?
স্যার অপ অ্যাম্পে যেখানে নেগেটিভ সাইন দেওয়া ওইটার সঙ্গে কেন পজিটিভ লাইন কানেক্টেড?
কোনটা?
মানে স্যার 0 ভোল্ট লাইন থেকে যেখানে যে মিট করছে বেসিক্যালি অপ অ্যাম্পে, ওইখানে আবার পজিটিভ লাইনটা কানেক্টেড হচ্ছে না?
আমি বুঝি না, আবার বলো। 0 ভোল্ট লাইন এখানে আছে, হ্যাঁ, এখান থেকে কোন লাইনটা কানেক্টেড?
স্যার আমরা মানে নেগেটিভ সাইড যেটাকে কনসিডার করছি ডায়াগ্রামে অপ অ্যাম্পের।
অপ অ্যাম্পে কোনো মানে এটা হচ্ছে নেগেটিভ সাপ্লাই, দিস ইজ নেগেটিভ সাপ্লাই।
স্যার ব্যাটারির কানেকশনটা তো বুঝছি স্যার, কিন্তু অপ অ্যাম্পে যে আলাদা করে তাহলে আবার কেন পজিটিভ নেগেটিভ দেখাইছে?
These are the inputs that we're going to
Why
feed
did
to the
we
op
need
amp
that?
so that it can do the amplification. It will do the amplification depending upon what is fed inside here. These are the two, these are called the input sides. This is the inverting input, this is the non-inverting input. This plus or minus sign don't have any
So
physical
those two are completely separate from the
supply. Yes, entirely.
batteries and everything.
Yes, yes, entirely. Those two are should be fed from the device or the signal that we want to amplify. This should be fed with the actual signal that we want to amplify. This is the additional help for the amplification process, and the output is the output. আচ্ছা, এখন এইটুকু হচ্ছে আমাদের ব্যাটারির কাবজাব. Now we're going to see that how does this circuit work and how the operation of the circuit happens. Now this is there are a couple of things that I need you to understand. Attention, খেয়াল করো. I should not move this much. Okay, moving this much is
So
good.
sir, এখানে কি এক একটা ইন্ডিভিজুয়াল ব্যাটারির ভোল্টেজ হচ্ছে 9 ভোল্টস?
Yes.
তো স্যার এরা যদি সিরিজে কানেক্ট থাকে তাহলে ভোল্টেজটা অ্যাড হয়ে যাবে না?
ওই যে আমরা তো সিরিজের ঠিক মিড পয়েন্ট থেকে মিড পয়েন্টে 0 ভোল্ট কানেক্ট করে দিয়েছি. The and if you connect a voltmeter across these 2 points, you're going to get 18 volt. No questions asked.
But আমরা জিরোটা রেফারেন্স, so that's acting as our reference point. আচ্ছা.
Exactly. Okay. How does a comparator circuit work? So this is the circuit for comparator. The name itself pretty much tells what this is going to do. Comparator is going to compare voltages. So to make work of this circuit, we're going to keep one of the inputs, either the inverting input or the non-inverting input, constant, and we're going to change the other one. Oh, thank you. We're going to keep one of them constant and we're going to change the other one. So whatever that is going to undergo the change is going to be the variable input from our device. That can be a thermistor, that can be an LDR, that can be a metal wire strain gauge, that can be a piezoelectric transducer, it can be a basic microphone, whatever. But we're going to keep one of the input constant so that we can compare with respect to that what is happening to the varying behavior. So we're going to add some additional parts to this circuit and see what's happening. So this is the actual circuit. You see, the complexity of the circuits are actually increasing, but don't worry. These circuits are elaborate because they have to be elaborate to make sense, but I'll make it easier for you. So first of all, my earnest request, don't be skeptic. Is that the word? I think. Don't be scared. I'm telling you this because when I first came across this thing, because I never studied these parts for my syllabus in any part of my degrees, I came across to study these parts and I understood and to a level that I could actually explain to you kids. So when I first came across this thing, I was pretty scared. That, what is this? And then I worked, I studied, and I believe I could reach to a level where I could actually transfer the idea to you. So don't worry, I'll help. Let's have a look at this circuit and break it down into pieces. We have the op amp over here. This is the supply, equal supplies over here. These two supplies, I mean, here, I need to understand one thing very clearly. If we assume, once again, that this is a 9 volt battery, this is a 9 volt battery, so this is a plus 9 volt supply in, this is a minus 9 volt supply in. In this circuit, this supply is doing only one job, is providing the minus 9 volt supply, nothing else. This battery is only responsible to providing the negative supply. It is not being used for anything else. However, this battery is providing three purposes. One purpose is it is providing the plus 9 volt supply to the op amp. Second and third is this 9 volt supply is also getting divided by these two vertical potential divider lines. So 9 volt, here you can see two resistors. So there is a potential divider circuit. Here you can see two resistors in vertical. There is a potential divider circuit. And the midpoint of these two potential divider points are drawn and connected to the op amp inputs. So here's the deal. This 9 volt supply, top one, is going to be responsible to provide this thing, which means this voltage is going to become divided over here, and then we're going to do some comparison. Now let me tear this apart piece by piece. Try to understand. Whenever we're going to do potential operational amplifier calculation, it is very important that you give plus sign in front of plus voltages and minus sign in front of minus voltages. It is highly recommended. In some cases, mark scheme, you can see that in some of the mark schemes, positive voltages are not given with plus sign, or maybe they have given plus in a bracket, showing that it's optional. But I highly recommend that you learn to write all of your voltages with the individual signs. It's very important. So let's break this apart. First of all, we have a total of 9 volt voltage supply over here. This is our 0 volt position. So this end is obviously plus 9 volt. So this point is plus 9 volt. You can see that within this vertical line, these two resistors are identical, R and R, equal voltage, which means this voltage over here will be divided into equal parts. So let's say the voltage of this point is going to be how much? Plus 4.5 volt. Do we understand this part? Because 4.5 equally ভাগ হবে, so এখানে 4.5 থাকবে, বাকি 4.5 এখানে ইউজ হয়ে ইমিডিয়েটলি এখানে 0 হবে। So এই পয়েন্টের, এই এক্সিট পয়েন্টের absolute voltage value হচ্ছে with respect to ground হচ্ছে plus 4.5 volt. This is just a very basic potential divider explanation. Then, which means for this connection of the circuit, our V minus will always have a fixed value. V minus in this case is going to be our, V minus means the inverting input is going to be our fixed input, which is going to be plus 4.5 volt. This is going to be fixed. Why is this fixed? Because this is taking, this is being drawn from the potential divider division of two fixed resistors, R and R, equal resistors. So this will not undergo any change over duration, and because they are not any physical factor dependent resistors, they're just fixed resistors. So this is a fixed voltage. So I am writing the word fixed over here. It is not essential that V minus will always be fixed. For this circuit, it is. Other circuits can have other properties. So don't take it as a rule of thumb. This is exclusive for this circuit only. Let's have a look at the V plus input. What's going to happen over here? Have a look. This is the non-inverting input of the op amp. This voltage value will come from the distribution of these two resistors. Now have a look. Here is a fixed resistor, F, and here is an LDR, which is RLDR. This LDR will be a light sensitive device, which means this one's voltage can undergo some variation depending on the light incident upon it. Now remember, high light brightness means low resistance, low light means high resistance. So let's consider those factors one at a time. Let's say in darkness, our LDR will be large, which means if you consider the voltage distribution between them, let's consider in this case, let's consider that our LDR is bigger than the F. If this one has a bigger resistance, if this one has a bigger resistance and this one has a smaller resistance, which means when 9 volt will be distributed across these two parts, this one will get a smaller portion of the voltage, this one will get a bigger portion of the voltage, which means this starting point above is actually plus 9 volt, this ending point is actually 0 volt. This will be consuming a smaller fraction of voltage, so it will be less than half, smaller fraction. So the voltage of this point is gonna be bigger than plus 4.5. So let's assume, just for the sake of understanding, let me assume that this one is consuming, let's say, maybe 3 volt, and let's assume that the voltage of this point is now plus 6 volt, and eventually LDR is consuming the remaining 6 volt, and it is eventually becoming 0 on the 0 voltage line. So now this point of voltage is, I'm considering it to be plus 6 volt. So I do not know exactly what values these things have to be to have this thing. Actually, I can find out the ratio, but disregard that. What I'm trying to tell you is that in this case, the LDR resistance is large compared to the F resistance. So the voltage value of this junction point is more than half, more than plus 4.5. So in this scenario, in darkness, let me give a bullet point, the V plus is bigger than V minus, which means V out is gonna be positive maximum, because V out is given by what? V out equals to gain into V plus minus V minus. So because V plus is bigger than V minus in this case, so output will be positive max, so that would be plus 9.0 volt or 9 volt. Bit more space. Okay. So এটা হচ্ছে একটা scenario. Oppositely, if we consider, let me do this, the other part in red. Oppositely, let's say whenever the LDR is kept in brightness, the LDR resistance would be small. So let's assume in this case the LDR resistance is smaller than the F, which would mean this is consuming a bigger fraction of the voltage, this is consuming a smaller fraction of the voltage. Just for the sake of discussion, let's assume now this one is consuming, out of the 9 volt availability, let's say this is consuming maybe 7 volt. So 2 volt is remaining over here, and then 2 volt is consumed by this one, so because this has a smaller resistance, so this is consuming less, and then it is becoming 0 over here after the consumption of the LDR voltage. This makes the V plus smaller than V minus for in brightness for the same circuit, because it's all happening because of the variable resistance of the LDR and nothing else. As a result, in this case, the output will also become saturated because it is an ideal op-amp. So as long as there is a difference between V plus and V minus, you will get a saturated output. In this case, the output will become negative maximum, which means this is minus 9.0 volt. So what is actually happening? What you can see that this circuit, based upon the illumination level on the LDR, it can detect whether the LDR is in darkness or the LDR is in brightness. And based upon that, it can give us two opposite type of voltage output. Which means if on the output side, we keep some signal mechanism, or we keep some actual components that we want to run, maybe a tube light or maybe a signal light. So here's the deal. If you want to, let's say, if you want to have a signal out of this circuit when the device becomes dark, for example, if you want to use this circuit, for a street lamp. Street lamp means that we're going to keep this LDR above the cover of the street lamp, which should be illuminated by the sunlight. So when the sun will come up, the LDR will be exposed to the sunlight, the street lamp should go off, and when the sun goes down, the street lamp goes on, which means in the darkness, the street lamp should go up, which means if we want to use this circuit to respond to darkness, or in the darkness, this circuit is going to give us a positive voltage, we can very easily connect a 9-volt LED light over here, symbol for an LED light over here. This is going to give us bright light, which might be as well be the street lamp, to give us the work. So this will only glow when the LED is in darkness, because in the darkness the output is positive, and this LED, which is connected over here, will only illuminate if it is having a positive output, because this is 0 volt, and if the output is plus 9 volt, only then can you have a current flow. But when the reverse will happen, when the sun will come up and the resistance, the LDR will have a larger resistance compared to the F, then this whole thing will revert and the output of the op-amp will become minus 9 volt, and then the diode will off. Now there is a question that how can we actually manipulate this circuit for different values. I'm going to talk about two types of changes that we can bring about to this circuit, and then I'm going to start taking questions from you. So whatever questions you have, please store them in your head. Don't forget them. I want to discuss two more things. One is that if you replace this LDR with any other sensitive component, for example, in this place of LDR, we can place a thermistor. This whole thing will become a temperature detector. In the place of an LDR, we can place a metal wire strain gauge. This whole thing will become a stress detector or strain detector. In this place, you can place a piezoelectric transducer, which is going to produce its own voltage. So that will give us a pressure detector. So you can input any component in the place of the LDR, which is capable of detecting a physical variation, which will lead this same circuit to give us two opposite outputs from the supply. Important information: for this entire circuit, the output will always be saturated, which means you're only going to get plus 9 volt or you're going to get only minus 9 volt. You're never going to get any value in between. This circuit is always working in saturation. This is one type of circuit that we use for op-amps. So that's point number one, that we can replace this component with other detectors and this circuit can work for those directions. The second point is that if we flip the position between these two, R, LDR and F, this whole set of equation will simply become reversed. So if you want an LDR to give a positive output in bright light, then you can simply place it over there and place this F resistance over at the bottom. Then this whole thing will become just reversed. There is another part for the second information, that is, we can fine tune this circuit that exactly at what illumination level, or if you say thermistor, exactly at what temperature this light starts to glow. I mean, up to which level of light this street lamp is not glowing, and up to exactly at what darkness this street lamp is actually going to start to give us light. You can fine tune this if we make this fixed resistor into a manually operated rheostat. So you can change the resistor value of the resistance to fine tune that exactly at what value of the light brightness value the LDR resistance and this resistance actually become equal, and then it crosses over the threshold. Becoming equal, I'm using the term becoming equal because you have to understand that for a certain duration this was happening, for a certain duration this was happening. So if you want to have a continuous change between these two things, there is a certain value for the illumination level for which LDR resistance becomes equals to F. There is a different value, and this is actually our boundary line. Whenever LDR resistance is bigger than F, then we'll have this. Whenever it is smaller than that, we'll have this. So this basically means our boundary. So if you want this whole circuit to work at different illumination level for different vendors, for example, let's say if it's a poor country, let's say our country is not that rich. If you want to have automation within these devices and we do not want so much light to be wasted, we might set this to a very much amount of darkness, that when the sun is really gone down, there's absolutely no twilight available, then this is going to light up. We can set it to that level. But in other places where electrical energy is pretty easily available, or they have moved mostly to the renewable energies and they have those things supplied. So they might as well move to much less amount of darkness, that whenever it is, let's say, about to become twilight, you still have the ambient light having, but it's gonna become dark, let's say in about 15-20 minutes, you're gonna have all the street lamps going up. So you can actually fine tune the exact sensitivity of this LDR, that exactly for what value this sweep or swap between big to small or small to big, this should happen. And to make sure that we have that flexibility, we can attach a variable resistor in this place, which can make this whole circuit usable for a wide range of users. I'll take questions. Abhias,
Sure.
Sir, this seems to do what a transistor does, but except more complicated. Doesn't it? Or are there more applications, more complex applications where the operational amplifier can be used where a transistor can't be actually? Sir?
I get your point. Hold up. Hold the seat. The example that I just gave you is one of the easily understandable application for an op-amp to work. But there are many other things that op-amp can do which a single transistor cannot do. If I give a very small observation difference, it might be a bit more clearer. The way a transistor works is that with the presence of a significantly large amount of base current, it opens up the collector emitter pathway, opens up that collector emitter pathway large enough so that significant current can flow by, and anything that is any electrical appliance that is connected in that branch will start to work. You will have a proportional ratio between the base current and the collector emitter current. That's how it works. For the transistor, you can have a device working or not working based upon the presence of the base current. But using a transistor, you cannot get two opposite type of voltages. You can have a device running, because that's the example of a transistor that we use that makes better sense. And here I used a similar example that we just want to turn on or off a light. But turning on or off a light is just one of the uses for where we can use this. We use a operational amplifier, but that's not the only use. The advantage of having an op-amp is that we can have two opposite type of voltage outputs based upon our input variation, which a transistor cannot give us. Transistor can control the current, whereas op-amp can give us a voltage output based upon the variation of the input. So there is difference in their working results.
So one amplifies current, one other amplifies voltage. Should I think like that?
Yes, yes, yes. You can precisely think it like that. So their output types are not same. But for my example, they pretty much does the same job, because I did not come up with a much more complicated example because it's difficult for me to explain with complicated examples.
I see, sir. Just another small thing, sir.
Yes.
Have electronic thermostats replaced the bimetallic strip things that we learned in O levels?
Yes, yes, yes. Electronic sensors have discounted bimetallic strip things in a lot of things, except for some few stuffs. For example, whenever in cases where we are dealing with a very high amount of heat, and we really don't want to rely on to the what can I say, flicking behavior of electronics. I mean, you have to understand one thing: a bimetallic strip is a robust thing that will do the job. An electronic sensor is a precise and sensitive device that will accomplish the job. But the problem of an electronic sensor is that in case of high current flow, large temperature variation, water damage, you can have this thing go not working anymore. It can have a lot of damage type issues. Bimetallic strips, unless it become rusted, it will always work. So in many cases, we use a bimetallic strip. For example, all the water heaters that you come across, which has an automatic switch off. I mean, you plug it into the electrical socket and then you press the switch, and when the water starts boiling, it simply goes off. All of those water heaters still work with a bimetallic strip because it is reliable, and you have enough heat available because it's a heater by design for the bimetallic strip to work. And also you don't have the electronics involved in most of these things because we do not have to control the temperature of a boiling water electronically. We want boiling water means when the water starts boiling, the water is hot enough. Do I make sense?
Yes, sir, that makes sense.
So one is robust, other one is precise, but one does the job and the one
Really does the job.
yeah, really does the job. Exactly. That's a good way to put it. Yes, Shubhro, go ahead.
স্যার আমি বলতে চাচ্ছিলাম কি যে why is it the মানে পজিটিভ যখন হচ্ছে তখন +9 ভোল্ট কেন আসতেছে, like why isn't it anything in between?
Because in this case, we are considering the ideal op amp. The gain of an ideal op amp is theoretically infinite. So no matter what value of difference that we have, the output will always be saturated.
মানে স্যার স্যাচুরেটেড বলতে হচ্ছে হাইয়েস্ট অ্যাম্পলিফিকেশন লেভেলে নিয়ে যাওয়ার চেষ্টা করতেছে।
Exactly.
আচ্ছা, আর একটা ব্যাপার হচ্ছে স্যার, মানে এখানে আউটপুট 0 হওয়া আর নেগেটিভ হওয়া এই দুইটার মধ্যে ডিফারেন্স কি?
আউটপুট 0 হবে যদি আমাদের এই ম্যাথমেটিক্যাল ক্যালকুলেশনের ভ্যালুটা 0 আসে, which means if by some mechanism V plus and V minus have the exact equal value, only then you will be multiplying this thing with a 0 value. Only in that case you can get 0 volts, which is highly unlikely to achieve if you actually have connected something with these things. You can have this thing becoming 0 if they are not connected with anything. If they are simply not connected with anything, you can have both of them to be 0 and the output will be 0. That's the typical output. But if you connect these things to two physical inputs, then having a steady 0 output behavior is pretty unlikely, which means you are always going to have some difference between them. So in some cases, one is V plus bigger or V minus small bigger, so you can have plus or 9 volts output. So your outputs will, in most cases, vary between +9 or -9 because it's very difficult or it's very unlikely to have these two values to be exactly equal for a prolonged observable duration of time. Because like I said in my earlier discussion that for this thing, for the output for an op amp, for a practical op amp which has a gain value of about 10 to the power 5, if these values have to jump in between this value visibly, it means if the output has to actually have a measurable observable value for a duration of time that is not +9 volt or not -9 volt, somewhere in between, the difference between these two voltages have to be within the range of 0.009 volt. No, another 0. This much. If the difference
এই রেঞ্জটা কিসের জন্য বললেন?
for the output not becoming saturated or to have any in between values, and that's also
exactly এটাই হতে হবে about
this is the maximum. Anything smaller than this also works. Anything bigger than this, it will have saturation.
Sir, is it always fixed যে এটা এরকম ভ্যালু আসবে?
No, this is not fixed. This is not a
9
value
ভোল্টের জন্য আমি এটা কনসিডার করতেছি 10 to the power -5
for a 9 volt supply and also for a typical real op amp which has a gain value of about 10 to the power 5. For this is for a real op amp value, but
মানে এরকম আলাদা আলাদা ভ্যালু সেট করা আছে স্যার, 10 to the power 3, 10 to the power 4 বা 10 to the power 5 এর জন্য।
Yeah, you can design op amps to have different of these values from your factory. You can, But we don't usually do that because that requires a very precise engineering. There is an alternative way to control this factor, which you are gonna see in a while.
Sir, যদি RLDR equals to F হয়, like how are we going to use it basically? Like will it help in any way?
In that case, the output will be 0.
So basically it's just turning off the whole system.
Yes. Turning off a device is also a function.
বুঝতে পারছি।
Okay. Anyone else? পোলামান বাকি সবার কি পার্টটা বুঝা গেছে? I'll bring up this whole thing and I would like you kids to read this part. It's basically exactly what I just said and see if you have any question from this part. I want all of you to read this thing. I'll give you 2 minutes. নুসাইবা নাইম এটা কে? আমি সবার চেহারা ভুলে গেছি, কতদিন তোমাদেরকে দেখি না। Rafid Abrar, I see that your microphone might not be connected, but I would like to ask you one question. You can reply in the chat. Did you find the PDF of the textbook? Did I send you those? Tell me yes or no in the chat, if possible. All right, that's about enough time to read through this thing. Any question? আমি এখানে additional একটা জিনিস বলি, for this circuit, because these two resistors were chosen to be of equal value, V minus was exactly half of the supply. For example, for my drawing, because these two resistors were of equal value, R and R, this was plus 4.5. This doesn't always have to be equal. Someone can send this to be as 1:2 ratio. If let's say R is 10 ohm and R2 is 20 ohm, then this would be 3 volt, because this will be plus 6 volt. So the value of this thing is dependent upon the value of the two resistors, because in this case these two resistors are equal. That's why this was half of that. In other circuits, for other practical reasons, they can have different values as well. In that case, the value would be here. One thing that I can always tell you, which can actually help you to understand, পোলামান এই জিনিসটা একটু ইজিলি খেয়াল করো, সেটা হচ্ছে যে নরমালি আমাদের নিচের রেজিস্টারের সাথে নিচের রেজিস্টারের যে ভোল্টেজ কনজাম্পশন, ওইটাই হচ্ছে এই পয়েন্টের ভোল্টেজ। হোয়াট আই টেলিং ইউ, এইটা যতটুকু ভোল্টেজ কনজাম করার কথা, এই পয়েন্টের ভোল্টেজ ভ্যালুটা হচ্ছে এক্স্যাক্টলি ওইটাই, বিকজ এই ভোল্টেজটা এইখানে কনজাম হওয়ার পরে আলটিমেটলি ভোল্টেজটা হবে হচ্ছে 0। So this is important and useful information for your calculation. For making better sense, I always talk about that this is going to consume one part of the voltage and then the remaining will be available over here. And to be honest, in all cases, that remaining voltage will be entirely consumed by this resistor. So if you are trying to find out the voltage value of this point exclusively by a single step, simply calculate the voltage that is supposed to be consumed by the lower one. This will make the calculations a bit more simpler. Okay, let's have a look at the next part.
So sir, if infinite impedance occurs here, মানে ওটা হওয়ার reason কি হতে পারে? What could be a possible reason for an infinite input impedance occurring here? মানে এখানে কি ওটা হওয়ার কোনো possibility আছে?
Ideal op-amp is assumed to have infinite input impedance, but practical op-amps don't. So actually, inside an op-amp, we have actually a lot of transistors and diodes all arranged together to give us this kind of behavior. The one way we can achieve infinite input impedance is that we can connect two opposite directional diode over here, so that there will be always a high amount of resistance across that thing.
So তার মানে স্যার সব ideal op-amp এর মধ্যে we have this high like infinite input impedance.
Yeah, ideal op-amps by theory have infinite input impedance. Real op-amps don't have infinite values because infinite values are not achievable. Real op-amps can have a very high impedance within a range of about 10 to the power 6 ohm to 10 to the power 12 ohm. That's a pretty large value.
Yes, sir, got it.
So it's important that you don't mess up the terms of real op-amps and ideal op-amps. You'll be handling mostly with ideal op-amps, but real op-amps are what is available for our regular life. So then comes the idea of negative feedback. Let me elaborate the part of negative feedback. The name itself, have a look, and you should be able to show an understanding of the effects of the negative feedback on the gain of an operational amplifier. I'm going to continue to this class a bit longer than 9:30 because I started late, because I would like to go to the end of this discussion. I usually always do these 3 circuits in a single class because it makes better sense. So it might be a bit longer than 9:30. I can see that many of the people have already left after seeing the working of the circuit. The participant number has reduced by 17 already. Okay, I don't blame them. The idea, first thing that I would like you to understand, negative feedback itself means that it will be working as a negative feedback. Now, what does this even mean? The idea of feedback is something like this. Is actually a flowchart for an ideal feedback. Let's say this is the direct way for an operational amplifier to work. So we have an input signal. Initially, we don't have anything to add because let's say for the very first input, we don't have anything to provide to this circuit, and then we'll have some output. We're going to take a small fraction out of this output and we're going to smartly add to the input side, and this is going to give us a secondary output. And this cycle can go on indefinitely till we get a stable output over here. So this is a very simple flowchart diagram for what the feedback fraction is. The basic idea is that we're going to take a small portion. Subru, do you have any question? I see your hand raised.
Sir, ভুল করে করছেন।
So the idea of feedback fraction is that we're going to have a basic output. We're going to take a small fraction out of it and add it to the input side to bring out some change in the output. So what kind of change are we expecting? এই জিনিসটা আমি এখানে আলাপ করব। So এখানে আমাদের amplifier মানে input fraction এর কিছু ক্যালকুলেশন দেওয়া আছে. This is actually pretty simple. I'll explain this from here. A fraction beta of the output voltage of the amplifier is fed back and added to the input voltage. The amplifier itself amplifies by an amount of A naught, whatever the voltage is present as input. So whatever you give, the amplifier simply amplifies it by A naught amount. The output voltage V out is given by V out equals to gain into input to the amplifier. Now in this case, whenever we have connected the feedback fraction, that input will not be V in only, it will be V in plus beta fraction of V out. This might be 1%, 2%, 3%, 25%, depending upon whatever you want to set. You will set this value over here, and this will give you a new input right over here. So this is the new input, total input in the presence of a feedback fraction or feedback mechanism present. And then if we just do the side changes and actually do the subject change of V out divided by V in, we get this fraction that in the presence of a feedback fraction, we get A naught divided by 1 minus A naught into B. Now, important for us to understand that this denominator is of somewhat value, and the original gain of the op-amp is going to be somewhat affected by this one. এই ইকুয়েশনটা প্র্যাকটিক্যালি আমাদের ম্যাথস করার জন্য খুব একটা লাগে না, so this is not a very needed information, but I want you guys to understand this replacement, because if you understand input amplifier, এই পার্টটুকু যদি বুঝো তাহলে এই ইকুয়েশনটা বানানো পসিবল। এটা থিওরিটিক্যাল ডিডাকশন কখনো এখন পর্যন্ত আমি কোশ্চেন পেপারে দেখি নাই, but this calculation is included in your syllabus, so you might as well just know that how this thing works. আচ্ছা, if the feedback fraction is negative, then the denominator must be greater than unity. If the feedback fraction is negative, feedback fraction negative মানে কি খেয়াল করো, এখানে 1 minus A naught B আছে, A naught is the open loop gain, which is generally a positive number. It's the ratio of, it can be negative. But if the feedback fraction itself is negative, if you can somehow make that thing to become negative, then this minus and this minus together will eventually give rise to a value that is positive. So this will have a positive value altogether, which means this denominator will be 1 plus something. If this beta itself is negative, we can, if we can somehow design this thing to become negative, altogether in the denominator will have 1 plus something, which means the denominator will become bigger than 1, which essentially makes the ratio value of this whole thing smaller than A naught. So we can somehow reduce the value of the gain of the ideal op-amp, and that's basically what we are after. Because here's the deal: if we want to avoid saturation, take a look at the equation. Let me just write this for you. Take a look at this equation. V out is equals to gain into V plus minus V minus. If we don't want to achieve, or if we want to avoid saturation, we either have to make this one small or we have to make this one small. Now, making this one small is not practical because this is an independent variable. This will be fed from the device that you're working with. So the only thing that we have left that we should be able to manipulate is this factor. So if we can somehow make this thing go down, then we can practically avoid the op-amp to become saturated. So all of this purpose of this feedback mechanism, and to be honest, negative feedback, is to avoid saturation. So how does this work? Negative feedback means, here you can see that feedback is always added to the inverting input of the op-amp. Why inverting input? Because, have a look, in this case, V out equals to gain into V plus minus V minus. If the feedback fraction is added to this thing, let's say I'm going to give a third bracket over here. Let's say this V minus is getting added as small fraction. Let's say this is X. আমার লেখাটা হইতেছে না, আচ্ছা আবার লিখি। Let's say V out equals to gain multiplied by V plus minus V minus plus X. So we're going to add a small fraction with the V minus, which means now the difference between them will become smaller. So if I try to give you a bit of an idea, let's say 10 minus 8 is 2, but if you can somehow do 10 minus 8 plus 1, that becomes actually 1. So if you can somehow increase the V minus, the total value of the V in can become smaller, and which can ultimately help us to avoid saturation. So negative feedback will always be attributed to the V minus end. This is a very important information, which will be useful for us in the next part. We are never going to provide the feedback to the V plus, because that will be positive feedback. We're always going to add the feedback to the negative feedback so that we can avoid saturation. Negative feedback benefit কি? এখানে আমাদের তিনটা বেনিফিট দেওয়া আছে, এই তিনটা বেনিফিটের এক্সপ্লেনেশন কখনো আসে না, so you can just remember / learn / memorize them. An increase of the range of the frequency over which the gain is constant, increased bandwidth. You can simply add increased bandwidth. It gives us less distortion. It gives us greater operating stability. I'm not going to go into a large amount of discussion about these things. This can be actually elaborated by a lot, but you don't need that for your syllabus. But if you're interested, I can give you to the direct you to the necessary study materials where you can actually understand more about these stuffs. So these are the three different stuffs that sometimes come up. That what are the benefits of a negative feedback? All right, 2 benefits or 1 benefit of negative feedback. You write any of these parts, you get one, you score 1 mark. And এই পয়েন্টগুলোর আর এদিকে আমাদের অপারেশনাল অ্যাম্পলিফায়ারের যে আইডিয়াল অপ অ্যাম্পের যে প্রপার্টিসগুলো ছিল, এই জিনিসগুলো পরীক্ষায় আসে। এই জিনিসগুলা স্টেটমেন্ট এবং এক্সপ্লেনেশন দুইটা ফরম্যাটে আসে। So you need to know the meaning of these parts. That's why it took so much time to actually explain these bracket information. But for this part, what are the benefits of negative feedback? You don't need explanation. You just want to have to remember these stuffs. Okay. I told you a bit earlier that we have 3 types of circuits. First, we have the comparator circuit. Then we have the inverting amplifier. This is the name. I'm going to highlight these stuffs before I do the printouts for you. So that you do not miss this out, or you can or you can highlight them with a highlighter. This is the inverting amplifier. This is the second type of circuit that we have to deal with. What does this second type of circuit do? Let's have a look. First, consider the structure of the circuit. We have a ground line. We are connecting the V plus directly from the ground line, which means V plus is a solid 0 volt. No questions asked, because it is directly fed from the ground line. Input voltage is going to be fed into the V minus. So that input voltage itself could be plus or minus, doesn't matter. But whatever your input, that is going to be fed into the minus side. Here we have a bit of a resistance Rin. Etar purpose ki seta pore boltesi. And then we're going to have the whole thing provided as output. We're going to take a small fraction of the output, make it flow to a feedback resistance labeled as RF, and connect it right before the negative input, not here. Before the negative input. And P is going to be one of our connection point, and this P point has a very important approximation based significance, which I'm going to explain. So এটা হচ্ছে আমাদের ইনভার্টিং অ্যাম্পলিফায়ার সার্কিটের স্ট্রাকচার। খুব ভালো করে খেয়াল করো, ইনপুট ইজ প্রোভাইডেড ইনটু দ্য ইনভার্টিং অ্যাম্পলিফায়ার। সো ইনভার্টিং অ্যাম্পলিফায়ার মিন্স ইনপুটটা ঢুকতেছে কোথায়? ইনভার্টিং অ্যাম্পলিফায়ারে। ফিডব্যাকটা বাই ডিফল্ট আসতেছে হচ্ছে ইনভার্টিং এন্ডে আসতেছে, because feedback will always be connected to the inverting end. এই সার্কিটটা খেয়াল রাখো। I'm gonna, before I get into the explanation, I'm gonna show you the other circuit so you can actually do a bit of a comparison. Sorry. This is the second circuit that we have, which is the non-inverting amplifier. Whenever it's a non-inverting amplifier, the input will be fed to the non-inverting input. Have a look. In this case, the input is fed to the non-inverting input. So take a difference. Take a good look at the differences. If I will place them side by side and make it a bit more wide, maybe. Okay, better visible. So take a comparison between the view of these two circuits. Here in the inverting amplifier, the input was getting into the inverting end. In the non-inverting amplifier, the input is getting into the non-inverting end. This is the key information by which you will be able to differentiate between these two circuits. And the feedback fraction is always connected to the minus. Here you can see, because the input was already fed to the inverting end, inverting input, so the feedback fraction was added to this, so we had an junction point over here. For this circuit, however, the feedback fraction itself is the V minus. So here is the output, here is the division of the feedback fraction. So this is the feedback resistance, this is the R1. In this case, there is no R in, because we don't need to have that. Here it was required. Here's the R1, so RF and R1. And from this midpoint, we are taking the feedback fraction out. And in this case, the feedback fraction itself is the V minus. So other than adding it, we are simply keeping the V minus as the feedback fraction. So like I said, for a negative feedback, the feedback fraction will always be connected with the V minus. In this case, because V minus was itself the input, that's why there was a additional join with the V minus. In this case, the input was fed to the non-inverting input. That's why the feedback fraction itself became the V minus. So feedback will be always attributed with the V minus end, or the inverting input. Whereas, is the circuit an inverting amplifier or is the circuit a non-inverting amplifier will be detected by exactly where that input is connected to. So if the input is connected to the V minus, it's a inverting amplifier. If it's connected to the if it's connected to the non-inverting input, is a non-inverting amplifier. That's the basic difference. Coming back to the question, there's that there is a bit of an approximation that we're going to do. Approximation means that we're going to define something as something which is not the same thing. For example, air resistance negligible. That's an approximation. For example, if you want to calculate the GP gained by an object, let's say above the Burj Al Khalifa, with a significant high structure, if you consider G to be same as the ground, just to avoid complication of calculation, that's an approximation. That we're assuming that the G at the level of Burj Al Khalifa and at the top floor of the Burj Al Khalifa, which is a very tall structure, they are same, but practically they are not same. But you can consider them to be same. That's an approximation. So basically speaking, avoiding some complication of the calculation and defining something a convenient thing so that we can avoid some complication is basically what an approximation is. Now, have a look. In this circuit, V plus is a definite plus. It definitely is 0 volt. If we want to avoid saturation, listen to the logic. To avoid saturation, V minus have to be very close to V plus, so that the difference between them, V plus minus V minus, is extremely small. So if I want to write them in terms of words, might as well take this picture out. Hoy nai. So in this case, we know for a fact that V plus equals to 0 volt. If we want to avoid saturation, V in should be extremely small. Extremely small, but not exactly small. That's why I'm giving the approximation, which means V plus and V minus should be very close to each other, almost identical. They should not be exactly identical, because if they're exactly identical, then the output will be 0. We don't want the output to be 0. We just want the output to be not saturated. So they have to be really close to each other. So the approximation is that V minus should be also approximately 0 volt. It's not exactly 0 volt, but because we want them to be very close to each other and V plus is definitely 0 volt, we are approximating that V minus should be also almost 0 volt. This is why this point P is called virtual earth. That's the name of this constant point. This is actual earth, 0, and this P point is called the virtual earth point. It has a benefit for us in the calculation, which we're going to see later on. So we're going to consider this point as a 0 voltage, and then we're going to see about some calculation. So a pointer implication দেখা যায় আমাদের এই দুটো সার্কিট খেয়াল করা লাগবে। এখানে আমরা দুটো ডিফারেন্ট সার্কিট দেওয়া আছে, and you will be, if you take a good look at one circuit at a time, have a look at the left circuit first. Here they are showing us that for a positive input we're getting a negative output, and for a negative input we're having a positive output. So you can see that there is a difference in arrow direction, which means their voltage types should be opposite of each other. One more thing. What? Virtual earth?
Yes, sir.
Acha. Okay. So that's that. And whenever so let's consider this thing. So we do not know yet whether this should be a negative voltage, negative output, but let's bear with me for the negative output point. Whenever we're going to apply some positive input over here, because no current can flow through the input side, you have to understand that the current flow will happen through this pathway. Or if we apply a negative input over here, where this is a positive output, current will flow through this pathway. So you have to understand that there is a difference between the positive output and the negative output. So this is the V in, this is the V out. The difference between these two voltages is basically the output voltage. And then again, we can consider the V in to be nearly 0. The V in to be nearly 0. So interesting idea. So this, we are going to consider for these figures, that the voltage of this P point is absolutely 0. For the sake of easier calculation, remember, the idea is very important. This is not actually 0. We are considering them to be 0 for the sake of easier calculation. What is that? What is that? What is that ease that we are referring to? What do I mean by ease of for the sake of easier calculation? Something like this. সেগুলো লাগবে না, হলো বাদ। Okay, something like this. Let's say at this point, the voltage of this exact point is 0 volt, and the voltage of this exact point is 0 volt. So what you can see that in this case, this is the high voltage. So I can write the current flow through this pathway is same all over. That's just Kirchhoff's first law. You cannot have different current flow through this pathway. So if we consider that current flow, for this resistor I can write V in divided by R in, which is the voltage over here. This is basically V in minus 0. V in, here is the V in, minus 0. This is the 0 volt divided by R in should be equals to 0 minus V out divided by RF. এই কোশ্চেনটা অ্যাপ্রিশিয়েট করা যাচ্ছে কিনা দেখো।
Sir, 0 minus V out কেন?
আম্মা আইদার শুইছেন অথবা রান্না করতেছেন। এখন
অলরেডি 6 জন রান্না হয়ে গেছে। আমি আপনাকে সুমন স্যারকে মুরাদ স্যার আমাকে পিক করব। সুমন স্যারকে নিয়ে আসছি, আপনি কি আপনার পিক করব?
5 মিনিট।
হ্যাঁ, আমি আসছি।
ক্লাসে ছেড়ে দেই।
ও সরি।
সমস্যা নেই।
আমি আসছি সামনে।
আচ্ছা, 5 মিনিট আসতেছি।
আমি সামনে আসছি।
ওকে, আমি যাব। I'm sorry. So V minus 0 divided by Rn equals to 0 minus V out divided by RF. Yeah, কি বলছো? আরেকবার বলো।
Which is 0 minus V out টা বুঝি নাই।
আচ্ছা, 0 minus V out হচ্ছে, for that I'm only considering the left circuit, so forget about the right circuit. Consider this one. This is the high voltage point, this is the low voltage point, because the output is supposed to be negative. So I'm subtracting high voltage minus low voltage divided by the resistance to give me the current.
আচ্ছা, হ্যাঁ স্যার বুঝছি।
ঠিক আছে, সো এই হচ্ছে ইকুয়েশন। আর এখান থেকে যদি দেখি, এখানে আমরা কি পাবো? Let's start from here. In this case, the output is positive, so let's start from the output part first. So I'm going to write V out minus 0 divided by RF should be equals to 0 minus V in divided by R in. এই হচ্ছে এক্সপ্রেশন। আলটিমেটলি এটাকে যদি সাইজ করি তাহলে পাবো হচ্ছে V in divided by R in. These are supposed to be subscripted, although it looks like V in, but this is supposed to be V out divided by RF. There should be minus sign over here, which gives me the V out divided by V in equals to minus RF by R in. And if we do the mathematical calculation over here, I'm going to get this exact same. I'm going to get this exact same relationship from this set of equation as well. This is the defining equation for the inverting amplifier. The reason is, and one important part of the inverting amplifier is that we have a minus sign over here, which tells us that the output voltage would be negative. এই ডেরিভেশনটা তোমাদের ইউজুয়ালি লাগে খুব কম, বাট কিছু কিছু কোশ্চেন এই ডেরিভেশনটা আসে। এই যে ডেরিভেশনটা এখানে দেওয়া আছে। সো এটা একটা ফিগার জন্য বলছে, সিমিলারলি সেকেন্ড ফিগার জন্য অ্যাপ্লিকেবল। সো আলটিমেটলি আমরা গেইন হিসাবে, যা রেশিও অফ দ্য আউটপুট এন্ড দ্য ইনপুট, এই গেইন হিসাবে আমরা পাবো হচ্ছে RF by Rin. So this is the key equation for the working of the inverting amplifier. Now, important information for you to see. Have a very good look. This has become our new gain, right? For this feedback mechanism. Do you see any presence of the anode over here? The original anode or the open loop gain that we are talking about. Do you see any mention of this thing? No. In this case, the gain is a redefined factor that comes from the ratio of these two resistances, which means you can conveniently choose the value of these two resistances, and whatever the ratio that you set will be your amplification factor, which means you can very easily avoid saturation. You can plan your gain value just by choosing these resistors as per your convenience. So by providing this feedback loop and considering this thing as 0 volt, we have practically thrown out the original open loop gain variable A naught out of the equation altogether. That's the beauty of the native feedback that we can have a much lower amplification factor, which is the gain, and that allows us to avoid saturation effectively. The second set of equation is here. A note-টাতে আমাদের second set of equationটা দেওয়া নেই, but you can very easily find out this second set of derivation in the McCandle book. Let me just show you that, and then we will call it a day. Oops, I zoomed out. Computer is going crazy. Sorry. Okay. So this is which chapter? It is about the index thing, so I have to look up from here. আমি কই দেখলাম আমার একটা বেরোবো একটু বল কমিউনিকেশন ইলেকট্রিক ইলেকট্রনিক্স এই যে এখানে হ্যাঁ পরে রাখো ক্লাস শেষ করে নেই 298 পৃষ্ঠা এই যে হ্যাঁ এখানেও তো এই ডেরিভেশন দেখা যাচ্ছে কি একটা বিপদ তাহলে এটা মনে তোমাদের অরিজিনাল বইতে আছে তোমাদের বই কোনটা এটা এখানে এটা আছে হচ্ছে electronics. AJ. So if you have a look at this circuit, in this case also, as long as the op amp is not saturated, the potential difference between the inverting and the non-inverting input is almost zero. So in this case, they are considering V minus and V plus to be nearly equal, because these two are supposed to be nearly equal to each other, so that the output is not saturated. So this is the approximation, because they are practically not supposed to be equal, because if they are equal, then input is zero, but it's not actually equal. Since the non-inverting input plus is connected to the input voltage, V plus equals to V in, and V minus is also equals to V in. So the gain is calculated from gain equals to V out divided by V in. So V out is the total voltage over here, and V in is the voltage across the R2. So in this case, we are defining the V in. So have a look at the pathway for the approximation. V in is V plus. To avoid saturation, V plus is V minus. V minus happens to be the voltage across R2. So ratio of V out divided by V in means V out divided by V plus means V out divided by V minus means total voltage across the R1 plus R2 divided by the voltage across the R2 only. That's why they simply gave this potential divider formula in right over here. So V out by V in this case is given by the total resistance divided by the remaining resistance, and that gives us 1 plus R1 plus R2. So in this case, it was mentioned as R1, and here in the other PDF, sorry, the PDF issue, here it is also mentioned as RF. The adjacent resistor they have mentioned as RF. It is an advantage to remember this as RF. The way I always teach the case, RF will always be on the numerator side, and RF will always be the one that is connected adjacent to the output. Adjacent to the output means এখানে দেখো immediately output এর সাথে লাগানো রেজিস্ট্যান্সটা হচ্ছে RF, এখানে immediately output এর immediate adjacent রেজিস্ট্যান্সটা হচ্ছে RF. So in this case, the gain is given by 1 plus RF by R1, and in this case, the gain is given by minus RF by R in. So that's basically the difference between the two set of power. And the important takeaway হচ্ছে, for both of these amplification values, it is only coming as a fraction of ratio of the resistances. So we don't have much problem to do. We can actually very easily achieve this thing. And another beautiful part of this whole thing is that we Sorry, another takeaway from this information is that in the inverting amplifier, the potential sign for the output and input will be opposite to each other. So if you, in the inverting amplifier, if you apply a positive input, you're going to get a negative output. If you give a negative input, you're going to give a positive output. Whereas in the non-inverting amplifier, you're going to get the same phase, which means positive input gives you positive output because there's no minus sign over here. Negative input gives you negative output. So these are the output variation of these two type of inverting amplifier. So I will once again highlight that there are three type of circuits for which you have to handle. One is the comparator circuit, which is one is the comparator circuit, which is something like this, or more precisely something like this. One is the inverting amplifier, which is going to look something like this. One is the non-inverting amplifier, which is going to look something like this. কিছু কিছু কেসে অনেক সময় একটা জিনিস হয় যে এই ফিগারটা কোশ্চেনে উল্টা করে দেওয়া থাকে just to avoid this overlap. So if they just horizontally flip this thing, the minus comes at the bottom and the plus goes on the top so that we can avoid this crossing. Sometimes they also set up circuits like that. So don't be bothered about that. Just keep a good look on the position of the plus and minus on the op-amp input sides and you'll be good to go. All right, I really have to close the class. It's late. And if you have any questions, I'll answer them in the next class. I'll upload the lecture in a while. And thank you very much. Allah Hafiz.